Hello, you're welcome back. Okay, so we're gonna be looking at Kirchoff laws. Okay, and when do we actually apply Kirchoff law? Now, previously we actually looked at the resolution of resistors in series and in parallel. Okay, they will solve some question where we are able to calculate the total resistance. And of course, apart from calculating total resistance, we're able to also evaluate the current passing through each resistor and their voltage. That's what we did previously. Okay. And that was, we're able to do that because we can resolve the network previously, the one we treated previously, into either series or parallel. But there are sometimes you will be given a network that cannot be resolved into series or parallel. Okay. You cannot resolve such network into series or parallel. So how then do you solve for the current passing through the components of that network, or even find the individual voltage drop, okay, across each component? So that is where Kirchhoff's law comes in. When you have such complex network, okay, or a network that cannot be resolved into either series or parallel, that doesn't mean that we can't use Kirchhoff law to actually solve a circuit that can be resolved into series and parallel. But Kirchhoff law is an extension that can help us solve more complex problems we that can be solved, okay, that cannot be solved by just resolving the network into series or parallel connection. All right, so now Kirchhoff law is being divided into three. We have Kirchhoff current law, all right, Kirchhoff current law, which of course is abbreviated as KCL, or you can call it Kirchhoff node law. All right. Then the second is Kirchhoff voltage law. Okay, KVL, or Kirchhoff loop law. Okay, let's just stick to KCL and KVL. All right. So now I'm gonna start with the very first one. Okay, this is actually a circuit diagram that I will use to illustrate these two laws. So let me bring it down first. All right. So now I'm gonna start with Kirchhoff. Kirchhoff's current law. Now, according to Kirchhoff current law, KCL, okay, the law actually states that the algebraic sum of the current entering into a node, all right, the algebraic sum of the current that is entering into a node, the one that is entering into the node, okay, is equal to the algebraic sum of the current that is actually leaving the node. So I in the one that is actually algebraic sum of the current entering into a node is equal to the algebraic sum of the current that is actually leaving that particular node. Now the question is, what is a node and how do we identify a node in a circuit? Now a node is actually the point in a particular circuit where, okay, the current actually branches. So invariably now, if I have, let's say, let me give this point. This is a point where current actually branches. Let me call it A. Let me call this B. Let me call this C. Let me call this D. Probably I'll call this EF. Okay. So now what am I trying to say? This point A is actually a node. Why? Because the source current coming from the source voltage, as it reaches this, let's say the source current is actually I. As it reaches this point A, this node A, what happened? It actually branches, it divides. Okay. So it divides. So some current will be entering to the resistor 6 ohm. So let me call the current entering to 6 ohm as I1. And of course, we have the one passing through 10 ohm to be I2. Okay. So according to Kirchhoff law, if I should actually express Kirchhoff law, right, from what I have from this circuit, I can simply say that the source current is actually entering to this node A. All right. As you can see, the arrow of the source current is entering to the node. While I2 is leaving the node, I1 is actually leaving the node, okay, by their arrow. So I can simply say that I is equal to I1 plus I2. So that is Kirchhoff current law. Okay, so please take note of that. Now, let's now go to the second law, Kirchoff voltage law. Kirchoff voltage law. Okay, so let me use a different color. Kirchoff's voltage law, KVL. KVL. What does it state? Okay. Now, according to Kirchhoff voltage law, it states that the algebraic sum of the voltage, all right, around a loop, the algebraic sum of the voltage drop, okay, around a loop is always equal to zero. So voltage drop, the algebraic sum of the voltage drop, okay, around a loop is equal to zero if you sum it up, all right? So now the question is, what's a loop? A loop is simply a closed path through which current actually flows, okay? A closed path. So something like you can get a loop with where you have a kind of a quadrilateral, okay, like a rectangle, for example. This is, you have this is a closed path, okay? Current goes, comes here, then of course returns back. This is a loop. This is also a loop, okay? So I can call this loop one. I can also call this loop two. I can also have another loop. Okay, let me clean up. I can have another loop. I have another loop. Current goes all the way, comes and return back to from where it is coming from. Okay, so those are actually the loops, right? So according to Kirchhoff voltage law, the algebraic sum of the current, okay, around a loop is actually equal to zero. So please take note of that. Algebraic sum of the current around, algebraic sum of the voltage, please. Algebraic sum of the voltage drop around the loop is equal to zero. So it simply means that in loop one, okay, if I should actually sum up the voltage starting from the source, flowing through resistor 5 ohms, then passing through resistor 6 ohm and returning back to source. If I should sum it, I should have, okay, it should be equal to zero. Now the question is, why should it be equal to zero? Okay, since none of this voltage across each of the components alongside with that of the source is zero, is because as you are summing it, okay, we are going to actually uh, be so careful with sign convention. Okay, that's what is known as sign convention. Some voltage drop, okay, is actually positive, while some voltage drop will be negative. So how do we know a positive voltage drop? And that's exactly what I want to explain now. Okay, so now let's see how we actually get to know a positive voltage drop. Let's look at first how current flows. Okay, now there's this controversy of how current flows, whether current flows from positive to negative or current flows from negative to positive. But let's just take it that, okay, normal convention is that current should flow from a lower potential to a higher potential. So let's take positive to be of a higher potential, while negative is a lower potential, right? So if current flows in the direction of, in this cell, from negative to positive, all right, it is actually, the current is rising from a lower potential to a higher potential, okay? So we'll call it voltage. So that means the voltage, when current flows from negative to positive, okay, that voltage is known as voltage rise. So that means the other way around, if the voltage is from positive to negative, that is actually voltage fall, okay? So, please pardon me. So now this is just through a battery. So which simply means that for my source, anytime I want to actually state the rise, the voltage across my source, okay, if I'm moving from the negative to positive, it's going to be positive, all right? That voltage will be positive, that because that's a voltage rise. Now what happens with resistors? Now, please take note that current will actually flow, okay? Current flows. Let's just get to the direction of the current. This is how current flows already. As the current flows, okay, the forest actually divides. I1 entered passes through the 6 ohms, while I2 passes through the 10 ohm, okay? So having known that now there's one thing you should know about resistors. Now, if you trace the direction of the current flow, if you trace the direction of the current flow, the very first point terminal that that current meets in a resistor is always positive. All right. So that means the very first terminal, this terminal 5 ohm is positive. All right. And of course, the other terminal is going to be negative. The same thing happens with the current that's entering to 6 ohm. The very first terminal of the 6 ohm resistor is positive. Okay. And the second is negative. So the very first terminal that current actually meets of a resistor, okay, in a resistor, it's going to be positive. So for the 10 ohm, this first terminal is positive, the other is negative. The same happens here. This positive and this negative, okay? So already we know that if we are moving in the direction from positive to negative, that is a fall in voltage. And a fall in voltage, we use negative sign to represent that voltage drop, all right? And if you're moving from negative to positive, that's a rise in voltage. And if it is a rise in voltage, we use a positive sign to represent that voltage drop. So let's actually see how we are going to do that. Let's start. Okay. So let's start with the very first loop. Okay. So starting with the very first loop, I want to actually evaluate K KVL in the first loop. So of course, this is loop one, right? The very first loop. So I can simply say that the voltage from the source from negative to positive, if I'm going, okay, in a clockwise, is that clockwise? Yeah. So that voltage, that 100 volt is positive. So as I move, I will encounter 5 ohm resistor from positive to negative. That will gonna be minus, okay? Minus, and of course, according to Ohm's law, voltage across the resistor is always the current of the resistor, then multiply by current of the resistor multiplied by the resistance, right? The current of the current passing through the 5 ohm resistor is I. Then of course multiply by the resistance, which is 5. Okay. So what I'm gonna have is 5I. So the voltage across 5 ohm resistor is gonna be 5I. Then I now go move, then I now meet 6 ohm resistor from positive to negative. That's still gonna be negative. Okay. And of course, we know the current passing through the 6 ohm resistor is 6, please pardon me. Okay, so that is going to be the voltage drop across the 6 ohm resistor going to be 6I2. So from Kirchoff law, the sum of all this voltage around this loop 1 is equal to 0. Okay, so I call that equation 2. Please pardon me. Okay, I call that equation 2. All right. So I have to rearrange this equation. How do I arrange this equation now? I'll take the current, okay? The expression that has the current to one side of the equation, then of course my voltage source to remain at one side. So if I take minus 5I to the other side of the equation, that's going to be plus 5I. The same thing happens if I take minus 6I2. Is it this I2 or I1? Please pardon me. The the current passing through 6 ohm resistor is I1. Okay, please pardon me. So that's gonna be minus 6I1 goes over, it becomes plus 6I1. Okay, and of course equal to 100 volts. Okay, equal to 100 volts. I can call that equation 3. But before I itemize that equation 3, remember what I told you that I, okay, the total current I is equal to I1 plus I2. So in that case now, this is going to be 5 multiplied by I1 plus I2. All right, then plus 6I1 equal to 100. Okay, that way I have to open this. If I open this bracket, this is going to be 5I1. 5I1 plus 6I1 will give me 11I1. Okay, if not that, if I'm not mistaken, right? That's 11I1. Now, of course, 5I1 multiplied by I2 will give me 5I2. So it's equal to now 100. Okay, so I call this another equation. Okay, called equation 3. Okay, this is for loop 1. So since it's for loop 1, let me call it equation of loop 1. Loop 1 equation. Loop 1. Okay, so let's go to loop 2. If I should go to loop 2, of course, this is my loop 2. Okay, so I go in the direction of the current. If I go this way, okay, that should be, is it anti-clockwise or clockwise? Okay, that's also clockwise, right? So if I go that way, now the very first resistor I encounter is actually 10 ohm with a current I2 passing through it, right? Current I2 passing through it. So, and it's gonna be, and that is positive, from positive to negative, that's gonna be minus. So I'm having minus 10I2, minus 10I2, okay? So here I'm dealing with, now what I'm working on is loop. This for loop 2. This for loop 2. So let me bring that down. Remember, what I actually evaluated here was for loop 1. Okay, this was for loop 1. Okay, so I'm going straight to loop 2. All right, so let's go there. So minus 10I2, then I'll go again. Current flows, it will encounter 8 ohm resistor from positive to negative. That's minus again. All right, voltage drop. So that's minus 8I2. Okay, so it still flows, the current flows, but I now enter into another branch. Okay, remember the current passing through this branch is I1, but now I'm entering it from, it will now, because I'm going in a clockwise direction, in this direction, right? So by going by that direction, it will, the very first terminal of this, okay, 6 ohm, it will encounter is negative, from negative to positive. All right, so that's gonna give me positive voltage rise. Okay, so in that case, that I'm gonna have, that's gonna be plus 6, and not forget the current. Okay, I1. All right, so everything according to Kirchoff, this sum is equal to 0. So let me simplify that. Let's simplify that. Okay, so of course minus 10I2 minus 8I2, that's gonna give me minus 18I2. Okay, then of course plus 6I1 is equal to 0. So if I should rearrange this equation now, I can simply have 6I1 is equal to 18I2. So if that being the case now, I can make I1 the subject of the formula. Okay, I1 is going to be equal to 18 I2, right? Divided by 6. 18 divided by 6. So that simply means that I1 is equal to 3 I2. So what is the whole idea of all this? Now you discover that with everything I've solved, now I have, okay, two unknown. What are the two unknown? From my first equation of loop 1 to the second equation now of loop 2. This is for loop 2. I have two unknown. What are those two unknown? I1 and I2. And I have two equation, okay? So if I have two equation and I'm having two unknown, I can solve for the two current, I1 and I2. All right, simultaneously. Of course, I know that you know how to solve simultaneous equation in Kirchoff law. Okay, definitely we solve simultaneous equation because Kirchoff law will always the expression will lead to system of linear equations. Okay, so if you know how to solve system of linear equations. All right, so now let's solve that. I can now solve that. I can solve it by substitution. To be easy, I will substitute I1 into equation of loop 1. Okay, so I will substitute I1 being equal to 3I2, 3I2, okay, into loop 1 equation loop 1. So let's do that. So if I get to equation loop 1, of course, this is my loop 1, 11I1. I'll have to substitute I2, okay? So that's going to be 11 multiplied by 3I2, okay? Then, of course, plus 5I2 is equal to 100. So 11 multiplied by 3, that's going to be 33. 33I2 plus 5I2, okay, is equal to 100. Okay, let's flow. Of course, this should give me 38. Okay, so I'm going to have 38, right? Yeah, I hope I'm not mistaken. I'm not. So 33I2 plus 5I2 is going to give me 38I2. So it's equal to 100. So what does that simply mean? Simply means that my I2 now is going to be equal to 100 all over 38. Okay, so let's work on that with calculator. Let's see what we got. 100 divided by 38. What do I have? So we'll have 2.6 ampere approximately. So that's, so if I2 is 2.6 ampere, how do I now get I1? Remember from this equation, okay, from loop 2, already said that I1 is equal to 3 times I2, okay? So that's going to be equal to 3 times 2.6. So let's multiply that. 3 times 2.6. What do I have? 7.8. Okay, 7.8 ampere. That is I1. Okay, now remember there are three currents. Then we have the general current, which of course is I, the main current. Okay, the main current I, we already know that is gonna be the main current I is equal to I1 plus I2. So which of course is gonna be 2.6 plus 7.8, or 7.8 plus 2.6 is still the same. All right, so well, let's add that together. 2.6 plus 7.8, so that's going to be 10.4. So that is Kirchoff law. So this is a simple application of Kirchoff law, Kirchoff current law, and Kirchoff voltage law. So I use this example to introduce, okay, the laws of Kirchoff. So we are going to work, okay, we are going to solve more questions, and I'm sure by the time we are done solving, let's say 2 or more examples, you get to understand how Kirchoff laws work. All right. Okay, so we'll do that in the next video. Right, see you in the next video. Thank you.